All right, so we're going to pick it up where we left off yesterday. So we introduced L'Hopital's rule, and the good thing about L'Hopital's rule is that it shows us how to take limits, even when it appears that it's not possible, because we end up with a result like 0/0, or possibly infinity over infinity. You might think, oh, that's it. The limit must be undefined, right? But that isn't necessarily true. It turns out that L'Hopital's rule lets us deal with situations like this. And basically, what it's telling us is that if you take the limit of a ratio of two functions, as you see here, and direct substitution results in 0/0, then what we can do is take the derivative of the two functions and try again. Now, it's possible that we'll still wind up with 0/0, but it may also result in an actual answer. So as soon as you see a 0/0, your first instinct should be try L'Hopital's rule. Now, even then, if L'Hopital's rule doesn't work, there may be something else you can try. But this is a very straightforward way of finding a limit when we end up with either 0/0 or infinity over infinity. Okay, now we did a few examples already. Like here, for example, you notice that when we took the limit as x goes to 0 of 1 minus cosine x over x, direct substitution gives us 0/0 because, as it turns out, the cosine of 0 is 1. And of course, don't forget, you can find this directly on your calculator. If you have, for example, the TI-84, the trig functions are directly above, well, 2 levels above the numbers. So you can just try cosine 0 and see what happens. And it does, in fact, come back 1. So that means in this case, we end up with 0/0. So don't give up. Not all is lost. This is a graph of the function, by the way, taken from Symbolab. And so remember what we're trying to do. We're trying to find the limit as x goes to 0, right here in the center. Now, if you notice, there's a hole in the function. There's a discontinuity there at 0. And of course, you can see why, because, x is in the denominator, which implies that the domain of this function cannot include 0. So we illustrate that with a hole in the function. But we've seen before, we had cases where limits were obtained even when there was a discontinuity in the function. Let's say, for example, we had something like this. We have some function, f of x, which has a discontinuity where x equals 3. So the limit of this function, though, as x approaches from the left, is actually equal to 4 because we never quite reach the 3 where the discontinuity exists. And that also, so it's coming from this direction, the limit is 4. But the same thing is true coming from the right. Okay, it's also equal to 4 because as we keep getting closer and closer, but never quite reaching the 3, the function gets very, very close to 4. So you might remember the two conditions we need for a limit to exist are, number one, the limit from the left. Oops, I wrote it wrong. The limit of f of x as x approaches a from the left must equal the limit as x approaches from the right. And we also require the function to be continuous everywhere. That was requirement number one, continuous everywhere. Meaning the entire real number line, except possibly x equals a. Okay, in other words, it's okay if there's a discontinuity at that point, we still will have a limit. As long as the limit from the left and the right are the same, whatever that number is, that's our limit. So our conclusion from all this is that the limit of this function, in spite of the discontinuity, as x approaches 3, is 4. So based on similar reasoning, with this case, there's a discontinuity at 0, but if you notice, the function is continuous everywhere except at this point. And as we approach from the left and the right, we're zooming in on 0, basically, okay? This is the point 0, 0. So as x approaches 0 from the left, should let me write this a little better. Is 0, and the limit as x approaches 0 from the right is also 0. So therefore, the limit, just from the graph, you can see that the limit, the two-sided limit, is 0. Okay. But L'Hopital's rule makes that even more clear. In other words, we don't have to look at the graph. We don't have to think about continuity. Once we take the derivative of the numerator and the denominator, we'll see we end up with the sine of x. And of course, as you can find out from your calculator, the sine of 0 is just 0. Okay. So in other words, L'Hopital's rule lets us prove that the limit exists and it's equal to 0. And I think you'll agree it's a lot simpler than analyzing the graph, although certainly that's a possibility too. But anyway, what about this one? Now, this one is a bit of a mess. Now, remember, too, I just want to make it clear that when you take the limit of a ratio like this, where the denominator is the variable, as x goes to infinity, the denominator is getting huge. So this ratio is converging to 0. That being the case, the limit of e to the 1 over x is just going to be e to the 0. Okay. Now, the limit of a constant is just equal to the constant. And of course, in the denominator, we have this. So we've got the limit is equal to e to the 0 minus 1 over 0. E to the 0, of course, is just 1. So we end up with 1 minus 1 over 0, 0 over 0. So it's time for L'Hopital's rule. Now, this time, it's a good thing we have it, because I think you'll agree finding it with this graph will be very tricky. Clearly, the function is discontinuous. There's two asymptotes. So here's what we're going to do. We'll use L'Hopital's rule with a quick reminder that the derivative of e to the g of x power from the chain rule is e to the g of x times g prime of x. Okay. I think we encountered this exact case when we were looking at the chain rule. In other words, you have to be careful with the numerator here. It's not e to the x, it's e to some function of x. So how do we take the derivative of e to the 1 over x minus 1? And how do we take the derivative of 1 over x? Okay, well, the denominator is a breeze. Because remember, 1 over x is just x to the minus 1. And by the power rule, we end up with negative x to the minus 2 power. We usually, when we use this power rule, we actually wrote it out like this, so that you have nkx to the n minus 1. But if there's no k, then this just simplifies to x to the n minus 1 power. And that's what's happening here. So the coefficient is 1, k is equal to 1. So this is our denominator. But what about that numerator? Yeah, this is one where we need the chain rule. By the way, we don't have to consider the -1 separately because this can be rewritten as we might as well do this right now. It might be a little quicker and easier to take the derivative of not the entire expression, but to break it up into two components. Because that's just going to go to 0. It's a constant. So for all practical purposes, what you're actually differentiating here is e to the 1 over x divided by the differential or derivative of 1 over x. Okay. So 1 over x could be considered to be a function of x. And just for convenience, let's rewrite it as x to the -1 power of g of x. And then that implies from the power rule, g prime of x is this. So based on the chain rule, we have the original e to the g of x, e to the 1 over x, and that's what we have here. And then you can rewrite this in a couple of different ways. You can move the negative out front, and then of course, x to the -2 power, as you recall, is simply 1 over x squared. I don't know if this is necessarily any more convenient than this, but that's what we have here. Now, we then have to still combine it with, remember, we still have this denominator. So we end up with, now this is a bit of a mess. So just remember, when you have a ratio like this, a over b divided by c over d equals a over b times d over c. So here you can think of this as having an implied denominator of 1. So I'm going to wind up with positive x squared. Oh, no, sorry. These are going to cancel each other out. I might as well just do that right here. There's two negatives that will cancel each other out. Plus, I've got these two. So I'm ultimately just going to wind up with e to the 1 over x. That'll be a lot quicker than what I was about to do. And then the limit of that as x goes to infinity is the same thing as e to the 0, which ends up just being 1. So after all that, the limit is 1. In spite of the fact that direct substitution gave us 0 over 0, we were able to persevere and discover that the limit is actually 1. All right. Now, I mentioned this before, we can also use the L'Hopital's rule when direct substitution gives us infinity over infinity. Like this, something like this. If I plug in infinity for x, I'm just going to wind up with infinity over infinity. That doesn't do me any good. So what do I do about it? Same thing. I'm going to take the derivative of the numerator and the denominator. So the second term is just 0. So we're going to end up with 3x squared over 2. The denominator so I'll end up with x squared plus 0, or just x squared. So now, when I plug these into the derivative, I've got 3 x squared over 2, all divided by x squared. Yeah. Let's rewrite this as x squared over 1. Okay, good. So then it's more noticeable that this is equivalent to multiplying by 1 over x squared. All right, and then these drop out and end up with 3 halves. So this divided by 1 isn't really necessary, but you know, if you have something like this, 3x over 4 over 3, it's equivalent of 3x over 4 over 3 over 1. And now I can rewrite that as, instead of divided by 3 over 1 times 1/3, and I end up with 3x over 12 or x over 4. All right, so we end up with 3 halves. And if you look at this graph, you can see there is an asymptote. Although it's hard to see from this graph, this asymptote is 3 halves, apparently. It's hard, like I said, it's very difficult to see it in this graph, but an asymptote will often end up being the limit of our function. Ooh, so now here's another one. It's going to give us infinity over infinity. Well, oh, look at this thing. Now that's not a very strange graph. So let's see what we end up with. So if you recall, the derivative of log x is very simply 1 over x. The derivative of 5x. You can rewrite that as 5 times the derivative of x. Okay. Oh, sorry, we're getting to, no, that's fine. It's just 5. The derivative of x with respect to x is 1. Sorry about that. So we end up with the ratio of 1 over x over 5. Again, remember, there's an implicit divided by 1 there. So we can rewrite this as 1 over x times 1 over 5, which is 1 over 5x. And so that's what we're actually taking the limit of. As x approaches infinity, we just end up with 0. Right? So in other words, all that algebra, all that calculus was to arrive to come up with the idea that we're actually just taking the limit of 1 over 5x. And so we just end up with 0. And I mean, you can kind of see that, because if you just imagine how this graph is behaving. Well, all right, it's not ever going to quite touch this vertical axis, but it's getting close. And so that's why the limit is 0. Okay, and then up here, it was 3 halves. Okay. So in other words, as you approach from the left, even though the function has a discontinuity here, so the limit as x approaches from either side is going to be 3 halves. All right, now we have seen that L'Hopital's rule works beautifully with 0 over 0 and infinity over infinity. Now, there's other so-called indeterminate forms that we might encounter, like 0 times infinity, infinity minus infinity, infinity to the 0 power, 0 to the 0 power. In these cases, we can't use L'Hopital directly, but what we might be able to do is do some algebra, which puts the limit into a form where it can then have L'Hopital's rule applied to it. So if you see one of these, don't give up. It doesn't mean that you can't use L'Hopital's rule, but you may have to do more work to get it to that point. So keep your eye open for these very bizarre cases. Now, 0 times infinity would be, let's say you have a product of two functions and one of them approaches 0. Oh, it's up here. The limit as x goes to a of f of x equals 0. The limit as x goes to a of g of x is infinity. So you end up with 0 times infinity. Now what do you do? Well, that doesn't do us any good. Man, look at this graph. This is very strange. Very strange. So what can we do about it? All right, well, we know that the limit of x, 1 over x to the n, as x goes to infinity is 0. And the limit as x goes to infinity of x to the n is just simply infinity. So here's what we're going to do. So the original function is 3x squared over x squared plus 1. We're going to divide the numerator and the denominator by x squared, the highest exponent in the entire expression. And we end up with the limit now of 3 over 1 plus 1 over x squared. Now that's good news because we actually don't even need L'Hopital because, as you know, the limit of as x goes to infinity of 1 over x to any power is just 0. And the limit of a constant, no matter what we're converging to, is just c. So that means that the limit, let me write this in the next slide because it's getting crowded. Um, 3 over So what that means is I'm going to wind up with 3 over 1 plus 0. So the limit ends up being 3. So if you notice, direct substitution gave us infinity times 0, which means we could not directly use L'Hopital's rule as it was written. But by the simple trick of dividing the numerator and the denominator by the highest exponent of x, we end up with an expression that can be solved directly. Very clever. By the way, what the heck? Let's look at this thing in Symbol Lab. It's always fun to look at these wacky graphs. X, where was it? Oh, 3x squared over x squared plus 1. Oh, we already had it. I forgot. We drew this thing. Okay, well, you can't tell by looking at this. Well, actually, you can. This dashed line, oh, there it is. The asymptote is y equals 3. So you see, no matter which direction you're coming from, this, as the limit is x goes to infinity, as we get further and further to the right, the function will be getting closer and closer to 3, without ever quite reaching it. So that's a hint that the limit is actually 3, but here is how we prove it. Okay, the graph is fine as far as it goes, and it gives us a hint as to where we're going, but we have to prove it with our calculus techniques. Now, this one's a little different because if you notice, the numerator is of degree 2 and the denominator is of degree 1. So the division, if we try to divide the numerator and the denominator by x squared, we're going to wind up with another indeterminate form, 3 over 0. So we don't want to do that. That's not the best strategy here. While we're thinking about it, let's see what this looks like. Oops. Yeah, I'll change it right here. Oh my God. Now that's a strange function. So what are we going to do here? Yeah, you see, this is what happens if you try to divide out by x. Actually, it's x. We didn't try x squared. Well, actually, x squared will leave us with 3 over 0. This is what happens if we divide out by the x. So you can see in this case, we actually did get an answer of infinity, which is a valid solution. I mean, infinity is, there's always a chance with any function that the limit is just infinity. So that is not considered to be an indeterminate form. So that's our final answer. That's it. We're done. And you can kind of see by looking at this graph, as x increases, this asymptote is also increasing. So it looks like the limit is simply infinity. Okay, because x will never stop rising, y will never stop rising. Okay, and that's it. We're done. But the trick here was this. We divided not by the x squared like we did here, because they were of the same degree. Because the denominator has a lower degree, we're not dividing by the x squared. We're going to divide by the x, the lower of the two. Now, that doesn't guarantee it'll be the final result that we need, but at least it'll bring us closer to the result that we're looking for. And then what about this case where the degree is actually higher in the denominator? Well, once again, we're going to actually divide by the highest power of x. And so by doing that, we end up with 1 over x over 1 plus 1 over x cubed. And of course, since we're taking x goes to infinity, that means we have a couple of zeros in here. And ultimately, our answer is 0. So let's try this graph. Now this is x cubed. Oh, every once in a while, I've had this experience with Symbolab. It kind of gives up. It comes back and says, these steps are not supported or something like that. Oh, here we go. I mean, there's a limit to what it can do. It's not, like I said, it's a free package. It's not exactly Mathematica, but it does a good job for the most part. Okay. So what they're referring to now, again, sometimes the way they draw these graphs is not maybe the best. We end up with 0. Okay, well, all right. Anyway, now, ooh, look at this one. This is actually a limit from the right, a one-sided limit. Why is that, by the way? It turns out, if you notice, the natural log, if you recall, does not include a zero. Um, if you take natural log of zero, it'll blow up. Because if you look at the graph, you can see clearly that there's an asymptote there where x equals zero, the vertical axis. And that's why the domain does not include the zero. So this is just some function of the log of x. Because this is here, we can't allow x to approach from the left. Okay, because all these values are undefined. Now, let's take a look at the graph anyway, just to see what it looks like. Okay, there's a hole there, but if you notice, it's not coming from both sides. All right. We've seen cases before where there was a hole in the function, but the limit was approaching the same value from both sides. That means there is no two-sided limit in this case, but there is a one-sided limit as x approaches zero from the right, so does the function. And we can prove it now. Direct substitution gives us 0 times negative infinity. We don't want that. So here's what we decided to do. We're just rewriting it in a very interesting way. Who would think to do something like this? And the beauty of doing it this way is all of a sudden, you now have negative infinity over positive infinity, which allows us to use L'Hopital's rule. Even though there's a negative up there, those are still both infinities. So that means that what we can do now is find our limit by taking the derivative of log x and dividing it by the derivative of 1 over x. And so we'll define g of x to be 1 over x, or x to the minus 1. Okay, so the limit as x goes to 0 from the right of f prime of x over g prime of x is the limit of 1 over x over negative x to the minus 2. Okay. So if you, let's see, we're going to have to rewrite this a little. It's a little awkward right now. Let me just move you to the next slide. Let's write it like this. Okay, that's a lot better. So therefore the limit is 0. Actually, let me write it like this. Since I went through all that work, let's make it negative x here. And that's, at long last, that's the answer. So there is a limit, as you can see, and it makes sense that it's going to be 0 because that's the vertical asymptote. And so that's it. We're done. So that was the case of 0 times infinity. Now, what about this case? By the way, each one of these cases is probably going to be treated a little differently. Infinity minus infinity. Oh my God, now what? So we have something like this, the difference between two functions, and as x goes to infinity, direct substitution gives us infinity minus infinity. Well, what do we do about it? It's going to depend on which of these two functions has the higher degree. Okay, so let's look at this case. So you've got f of x is 3x cubed, g of x is 3x squared plus 5. The limit of the difference is the limit as x goes to infinity of 3x cubed minus 3x squared minus 5. Now, if I directly substitute there, well, this is no good. So if, now here's what, this one is growing more quickly than this one. So the logic is that if that's the case, then the actual limit here is just positive infinity. All right, because you've got two terms. You've got a term that's getting large very quickly, and you're subtracting a term that's getting large not quite so quickly. Forget the constant, it's just the same all across. But it stands to reason that the function will eventually reach infinity. In fact, why don't we look at this in Symbolab? All right, so we have 3x cubed minus 3x squared minus 5. Yeah, I mean, look at that thing. It's pretty clear by looking at the graph. It's just going to infinity. Well, if that's the case, what if both of these two terms have the same degree? Why don't we just look at this on the graph first? Oh, well, that was a bad choice because yeah, they're both we're gonna wind up with just a constant. You know what? Let me just try this. Let me try a different coefficient. Oh, of course, that's a problem. Okay, but the bottom line here is that you've got two expressions that are both converging to infinity, and one is being subtracted from the other. So what's left, this -5, ultimately ends up being our limit. And then finally, we have the case where the second term has a larger degree than the first. So let's look at Symbolab for a second. This is now just 3x. Ah, it looks like we're going to have a specific constant again. Negative infinity. Oh, I see what they're saying. Yes. No, that's the maximum point. The limit would be negative infinity because it's going down in both directions, all the way down to negative infinity. Okay. So we end up with another one of these. And so we've got a larger function being subtracted from a smaller function. And again, it stands to reason that we're going to wind up with negative infinity. All right, one more of these. How about infinity to the zero? So L'Hopital's rule applies to ratios. So an indeterminate form involving exponents could be rewritten as a natural log. So we're going to try that. The limit of y equals f of x to the gx power. We're going to rewrite it as e to the L power. So here, for example, y will be 1x to the 1 over x, which based on the properties of logarithms can be rewritten as 1 over x log x or log x over x. So the limit of the log of y, okay, so this is y. Is the same as the limit of this as x goes to infinity. Okay. So of course, what we can do here, we take the derivative. Oh, this is so easy. So we end up with 1 over x over 1. And of course, as you take the limit as x goes to infinity, this goes to 0. And we end up with 0 over 1, which is 0. Now, because that was the y, the log of that brings us back to the log of x, which is 1. So in other words, think of this as the log of y equals 0, log of x must be 1. Okay. All right. Now there's others too, but we're just going to focus on these. So that is our discussion about L'Hopital's rule. So as soon as this thing is saved, I don't want to lose it. We're going to look at D. Now we're going to try start something completely different here. So we know that, let's say, for example, oh, actually, this is what they're doing. If f of x is x squared, we know that f prime of x from the power rule is 2x. We say that 2x is the derivative of x squared. Then we can say in turn, x squared is the antiderivative of 2x. In the same way that if the sine, let's say of 90, I think it's 1. Hold on. Yeah, the sine of 90 is 1. Then the arc sine of 1 is 90. It's the same relationship here. So 2x is the derivative of x squared, which implies that x squared is the so-called antiderivative of 2x. Now, I do want to mention here that the word in math, antiderivative, is often used interchangeably with the word integral. Okay, I just want to mention that right now because we'll run into it very soon. You'll see that the book will start just calling them all integrals. Now, you'll notice here that notation-wise, we're going to use the following. If f of x is 2x, we just got through showing that f of, let me just quickly remind everyone, 2x is the derivative of x squared, which implies that x squared is the antiderivative of 2x. So if the original function was 2x, capital F is the antiderivative of f of x. And what this is telling me is that if I take the derivative of the antiderivative, it sounds very strange, equals the original function. In other words, if I take the derivative of this capital F of x, I'll end up with f prime of x, which is the same thing as the original f of x. Okay. Now, taking a derivative, now this is where it gets very strange. If you take a derivative, you'll get a unique solution, okay? So in other words, the derivative of x squared is 2x, end of story. But if you notice, the derivative of x squared, let's say plus 1, is also 2x. Oh my God. So what this means then is that 2x can have an infinite number of antiderivatives. So what we often do to represent this fact, and by the way, if you notice though, the only thing that separates them all is this constant. The x squared is the same for all of these, but there's that constant there. So you could make the case then that x squared plus some arbitrary constant c is the antiderivative of 2x. Yeah, this is where the two, notice the two are inverses of each other. But if you notice, when we take a derivative, there's of a function, there's a single result, but antiderivatives are different. There's an entire family of antiderivatives that will all bring us back to the same function. And the only thing that separates them all is a constant. Anyway, so let's try this. What is the antiderivative of f of x equals 3x squared? Well, you see here, what we're doing here is we're not actually showing you how to calculate antiderivatives. We're just illustrating this relationship. If you took the derivative of x cubed based on the power rule, you would get 3x squared. That means the antiderivative, 3x squared, is x cubed, but we also have to include that c, which, by the way, could be 0. So f of x is 3x squared. The antiderivative is x cubed, and we have to include that constant because we know there's an infinite number of possible antiderivatives that would all give us the correct result, all of which are the same except for the constant. Okay, now here's another one. By the way, you're probably wondering, how do we know that x cubed was the right choice for this antiderivative? We're going to learn a lot of rules in the next chapter to help us figure out antiderivatives. Okay, but here it's what we're just trying to point out is that if you were starting out with f of x is 1 over x, the antiderivative is the natural log of x plus c, because the derivative of log of x is 1 of x. And then, of course, you need the c. Again, so we'll learn how to find out for ourselves what is the correct antiderivative. Now, when it comes to logs, we often have to make restrictions. If x is positive, then the antiderivative is log x. Otherwise, it's negative, 1 over negative x. So for that reason, with this one interesting case, yeah, the antiderivative of this function we have to take into account the possibility that x was negative. Either way, we're going to wind up with the same result. So we're going to end up with, we're going to use the absolute value sign to show this, okay? So if x is positive, and so in general, the antiderivative of 1 over x will be log absolute x plus c. That's one of the unusual cases. You'll also run into this with some of the trig functions. Okay, here's a straightforward one. Because in other words, if forget the constant, its derivative is 0. If I take the derivative of sine x, it gives me cosine x. Therefore, Sine x must be the antiderivative of cosine x. And of course, don't forget the c. All right, I think there's a couple more here. Ooh, look at this one, e to the x. So the derivative and the antiderivative are both e to the x, but here we do need the c. Now, antiderivatives, like I said, the word integral is often used interchangeably with antiderivatives. And so we're going to introduce a brand new symbol here where we're taking the integral or finding the antiderivative of f of x is the same thing as saying finding the integral of f of x, or sometimes we say integrating f of x. And the symbol we use for that is this thing. And also, when you do take an integral like this, we need this extra term dx. It represents what we're basically doing with an integral. Let me just quickly sketch this out for you. And we'll get into this discussion in great detail in a few minutes. Let's say you were interested in the integral of this function between this interval a and b. That equals the shaded region under that curve. Now, you can approximate this curve by imagining a series of rectangles. That we construct between a and b. Now, the heights of these rectangles would be f of x. The width is what we're going to call delta x. The area is the sum of the areas of the rectangles. Whereas each rectangle has a slightly different area. They're the same width, but they all have different heights. So each one we calculate and we add them up. Now you can see that's only given us the approximate area under that curve. And so the logic behind all this is that as we shrink up the width between of these intervals, these rectangles, in other words, as we have more and more rectangles that are progressively less wide, in the limit, delta x becomes dx. The height of the curve is just f of x. So think of the integral. This is in effect an infinite sum of rectangles. So in other words, instead of having a finite or a large number of these rectangles whose area, whose area equals the area under this curve, with the integral, you've got an infinite number of these rectangles. So that's why that notation looks the way it does. Okay. And in fact, I don't know if anyone knows that this is true or not, but some people think that this is meant to be used as an infinite sum because it's kind of similar to something like this. I don't know, it's not that close. But the two supposedly, one comes from the other. But that curvy symbol looks like an S is used to represent infinite sums, and we'll use that to represent integrals or antiderivatives. And oh, and by the way, one more thing, we can solve for the area under this curve by evaluating f of x over that interval. Okay, so we'll get more into this as we go along. We're getting a little ahead of ourselves here. So what we want to do is start to learn some of the rules for finding these integrals or antiderivatives. So we'll start with the power rule. Now for derivatives, as you recall, the power rule is d dx of x to the n is x to the n minus 1. If we work this backwards, the integral of x to the n power dx is x to the n plus 1 over n plus 1. And of course, we always need the c here. The only thing we can't have here is negative 1. Okay, this one has its own rule. So every other case can be solved like this. So here's a quick example. I'll copy this into the next slide. Okay, x to the fourth dx. So this is our n. Here's n plus 1 over n plus 1. And so we end up with x to the fifth over 5. And again, don't forget the constant. Okay. So that's the power rule for integrals. Now, how about this one? This one's a little trickier because of a negative exponent, but it's still the same logic. So negative 2 plus 1 is here. Negative 2 plus 1 is here. Don't forget the c. So we end up with x to the minus 1 over negative 1, or simply negative 1 over x plus c. By the way, if you're not sure if you've done this correctly, you can double check by taking the derivative of your integral. Like here, for example, you don't have to worry about the constant because we know that the derivative is just 0. Whoops, I did something wrong. Let me just sneak in here the power rule for the derivative. But 5 times 1/5 drops out. And we end up with our original function, x to the fourth. So that means we must have done this correctly. All right. Let's see. Now, the integral of a constant will end up being kx plus c. Because implicitly, you could rewrite this as kx to the 0. And there you go. Also, I just want to point out too, and we'll see a lot of this as we go along. This can be rewritten as k times the integral of dx. For some applications, it might be easier to move the constants on the outside because it might be easier then to figure out what rule you're supposed to use to solve for this particular integral. Oh, speak of the devil, look at this one. If I chose to, not that it's that important, I could have done this. And since we just saw the integral of dx is just x, and that's it, we're done. Yes, and I just mentioned this, you can factor out constants, and so the power rule here would be x to the 6th over 6. And when you have your 4 here, of course, never forget the c. So ultimately, you end up with 4/6 x to the 6th, or that reduces nicely to 2/3 x to the 6th. Okay. So that rule you just saw, the power rule, is perfect for polynomials. But what about other more complicated cases? All right, so I tell you what, now this is towards the end. This is, I believe, the last part of 4D. What follows in chapter 5 is just more discussion about integrals. So I think we'll stop it right here. And when we come back, we'll pick it up with more complicated rules for integration. And then we'll dive into 5. We'll see even more. I think chapter 6 is applications of integration. But for 5, our attention will be 100% focused on learning the rules of integration. All right, so I'll see you all next time.